let's spend some time talking about alpha alkylation. And we might want to take a ketone and put another carbon group on the alpha position. So in this case, you can see we've added an ethyl group to that alpha position. And one way to do that is via quantitative deprotonation using LDA, and then taking that anion and alkylating it with ethyl chloride or ethyl bromide in this case. Wow. So the requirements here, we need a good SN2 electrophile. So you can't use like a tertiary chloride or a tertiary bromide. And we want to use LDA to quantitatively deprotonate. So LDA gives us irreversible deprotonation. And what the point here is that no base remains to act as a nucleophile. And I'll show you what I mean here. What if we had this situation? Hydroxide plus acetone. And we know that that's going to deprotonate. But it's also going to be in equilibrium. And if you look at the equilibrium here, the pKa of acetone is somewhere around 19. The pKa of water is somewhere around 15. And so we're going to have a pretty equal amount of both. There's going to be some of each of these bases present at equilibrium. There'll be some of each of these acids present at equilibrium. And so if I were to take this whole thing, right, this equilibrium mixture, and react it with ethyl bromide, like I did on the previous slide, we will get some ethylation of the alpha carbon, but we'll also get some ethylation of this strong base, strong nucleophile, which means we make ethanol, which is probably not our desired product. We can buy ethanol very cheaply. We don't need to make it in the lab. And so that's why we need to use a very strong base, such as LDA, to do our deprotonation so that we don't have any equilibrium. We drive everything to the enolate side of the equation, and then that enolate can preferentially react with our alkylating agent. We don't have to worry about the base reacting with that. What if we have a symmetrical, unsymmetrical ketone? We can react this with LDA, and under certain conditions we can favor one side or the other. So we might expect this or this enolate. And this would be the thermodynamic product. And this would be the kinetic product. If you remember that the LDA is a large non-nucleophilic base, so it's going to be easier for LDA to remove alpha hydrogens that are not sterically hindered, such as the ones on the left side here versus the ones on the right side. And so at higher temperatures, say 25 degrees room temperature, we might get the thermodynamic product. And at lower temperatures, minus 78 degrees, which is a more common temperature for LDA usage, we're going to get the kinetic product, the easier hydrogen to access. So you see here, you can sort of control which side you're going to alkylate depending on the temperature you allow your LDA reaction to occur on. So let's look at another option for basically alpha alkylation. And I want you to think about this in terms of taking an alkyl halide, again one that can perform SN2 reactions well, and extending the chain by 2 carbons and ending up with a carboxylic acid. So 2 new carbon atoms. And we've learned other ways to extend the chain by 2 carbons. Remember, if you turn this into a Grignard, react it with a epoxide, you can extend the chain by 2 carbon atoms and end up with a alcohol, primary alcohol, which we could then turn into a carboxylic acid. So this is just another way to get there, and it is a little bit easier. It doesn't require as harsh conditions. So what we're going to do is we're going to use diethyl malonate as our starting material. And I'm going to draw it properly for you. Really, the R group of the ester is not important, because as you see in our final product, it doesn't exist. So you could use dimethyl malonate if you wanted to. Really, the importance is that we have this doubly alpha hydrogen right here. So what I'm going to do then is react this with ethoxide. and that's going to deprotonate, as you might expect, on that reasonably acidic hydrogen, just like we saw in the Claisen reaction. And then I'm going to react that with my desired alkyl halide. Again, needs to be a good SN2 substrate. So there's my 3-carbon chain that I just added here. We are in base, so the possibility exists that we might remove that H as well. But that's because that means we'll follow this up with mild acid workup. And as we learned in chapter 21, if I use acid and water to hydrolyze esters, I'm going to make carboxylic acid. So that's going to be the product of this step. And the interesting thing about this is a beta dicarboxylic acid. So we have 2 acids in a 1-3 relationship. If we use heat, we can lose one of those carboxylic acids in the form of CO2. So that's quite interesting. So let's look at how that might occur. We actually don't need any more acid in this case. We just need to redraw our molecule in this fashion. And then we need to draw a mechanism that makes a new OH bond, makes a new CO double bond, and breaks this CC bond so that we can lose CO2. So I'm going to circle what's going to become CO2 in red here. So that's going to be our CO2 piece. And we make this, basically it's an enol of a carboxylic acid. And you can see how the enol, again, we've got an ene, an OL, we've got an alcohol and an ene. We have an additional alcohol because we started with a carboxylic acid. But under acidic conditions, we can tautomerize this. And we drew mechanisms for this earlier in this chapter. I'm not going to reproduce that here. But suffice it to say, we make this product. And I hope you agree that this product up here is identical to the product we just made. And so basically the overarching concept is that we can take any good SN2 candidate, alkyl halide, extend the chain by 2, and end up with a carboxylic acid on that position. We could also essentially alkylate malonic ester twice to put 2 different alkyl groups on our alpha carbon position. So the first step, ethoxide. Second step, our alkyl chloride or halide of choice. Third step, deprotonate again. As long as we have 2 hydrogens here, we can deprotonate once, alkylate, deprotonate again. And let's use just a more interesting one, maybe benzyl bromide here. And 5, acid workup, heat, allows us to decarboxylate like you saw on the previous slide, and we end up with where our original 2 carbons comes from here. No. So there's our original 2 carbons, and you can see that I've added the ethyl group, 1, 2 carbons here, and the benzyl group, the phenyl with a benzylic position added as well. And so now I've taken my carboxylic acid and added 2 different R groups in a multi-step sequence. Now I could have added the ethyl group 4th if I wanted to, and added the benzyl group 2nd. It doesn't matter. The order is not important. But the interesting thing here now is I have a more interesting carboxylic acid that I can eventually maybe turn into an amide based on reactions I learned about in the carboxylic acid derivative chapter. I could reduce this to an alcohol and then I could do chemistry on that alcohol. So I'm being able to more increase the complexity of my substrates. And one final example is the acetoacetic ester synthesis. And this is going to be very similar to the malonic ester synthesis, but in this case we end up with a ketone. So let's take that same 3-carbon alkyl halide, and you can see here my 3 carbons basically getting added to acetone. So this is a way of functionalizing acetone, or increasing the acetone carbon chain and giving us a larger ketone to deal with. So we would work on this one very similar. We'd start with an ester on one side, ketone on the other, deprotonate the same way, add the alkylating agent, then H3O plus will hydrolyze the single ester, heat will decarboxylate that single ester, and we end up with, and if I can put a red dot here just to keep track of that carbon, that's going to be the same carbon right there. So you can see that instead of the carboxylic acid functional group that we end up with, in this case we end up with a ketone, essentially a small ketone that has become larger via this alkylating agent. I'd like to point out here that this has the same mechanistic steps as with the malonic ester synthesis, just a slightly different starting material, and we can also doubly alkylate as we saw on the previous slide. Let's look at one example here. How might we synthesize this molecule using some acetoacetic or malonic ester synthesis? Think about that for a few minutes. All right, so if we're asked to create this molecule, we might first decide that it is a ketone. So we'll use the acetoacetic ester synthesis, which means these 3 carbons that I've circled come from the acetoacetic ester. And let's draw that here. Again, the O-ethyl doesn't matter, it could be O-methyl. And we see that we're going to put 2 R groups on, so let's go ahead and do that. First step would be deprotonation. Second step, one of the R groups. Third step, deprotonation again. Fourth step, the other R group. This one might be a little more challenging because it is a secondary substrate, which doesn't react quite as well in an SN2 fashion. And lastly, hydrolyze the ester. Heat will drive off CO2. We will lose this portion of our starting material, leaving us with, I'll try to circle that in red again, these 3 carbons are going to be still present in our product. As you can see, I circled them over here. So we can now basically create a much more complex ester under relatively mild conditions. This base doesn't require high temperatures to deprotonate. It's not an extremely strong base like LDA. It's not that expensive. These alkylating agents are pretty cheap. They're easy to come by. They don't require harsh conditions either. So this synthesis allows us to use less harsh conditions than with LDA and still get some alkyl groups at the alpha position on a ketone or on a carboxylic acid.